Okay, so we are now in chapter 5. Okay, because week 5 actually the first chapter was on the introduction, and then second one was thermodynamic principle, the pressure, temperature, those parameters, and then the third chapter is actually I already combined the third and fourth. It's about the pure substance, okay, the solid, fluid, and some of the diagram, ideal gas equation of state. I have introduced that last week as well. So those actually are combined between chapter 4 and 5. Oh, I forget to modify the title of my slide. Okay, it's okay. Again. So now actually it's chapter 5, okay, because I've already combined the chapter 3 and 4 together because it is still about pure substance. Okay, so now so this chapter 5 will be on the energy transfer on heat, work and mass, and next week inshallah another chapter on first law of thermodynamics. Okay, actually I already mentioned a bit here and there about this first law of thermodynamics. So next week just more on the application. Okay, and then we will do tests, and second half of the semester we'll see on the second law. Okay, so this one chapter 5, energy transfer by heat, work and mass. Okay, so introduction, again, some of the definition that you need to recognize, that you need to remember. Heat, what is heat? Heat is the form of energy that can be transferred from one system to another as a result of temperature difference. Okay, whenever we have temperature difference between two solid or two materials, two substance, here we use the word substance, but it is like material or solid, etc., fluid. So in between two substances, there will be this heat transfer process phenomenon. Okay, whether it is slow or fast, that depends on the difference of the temperature and the power or extra power that we put into the process. Okay, but whenever we have a temperature difference between two materials, then there will be a form of energy transfer, heat transfer between those two. Okay, so even though you didn't put any power, any electricity, there will still be this heat transfer process naturally. Okay, and then thermodynamics. So thermodynamics again concerned about the amount of this heat transfer as a system undergoes a process from one equilibrium state to another. So why we need to learn why this heat transfer is very important topic in thermodynamics or aerothermodynamics. Okay, it's because in thermodynamics we take into consideration, we take into account the amount of this heat transfer. Okay, so it's one subtopic in the thermodynamics, thermal, okay? And the heat transfer deals with the determination of the rates of such energy transfers as well as the variation of temperature. Okay, so actually the heat just now, the first sentence, the first point, the heat is the form of energy, and the heat transfer, the process, okay, is the rate the rate of the energy transfer process between those material, those substance, those fluid. Okay. The transfer of energy is always from the high temperature medium to the lower temperature one. Yes. Okay. So once we have the difference of the temperature, so the direction of the heat transfer, it is always from the hot side or hot fluid to the cold side or cold fluid. Okay, it shouldn't be the other way around. Not from cold to the hot. It's from the hot to the cold. The hot medium is the one who are going to transfer the heat. Is the one is going to give. Okay, and the colder side, the colder medium is the one who is going to receive or absorb the energy. Okay, naturally it's that way. And then heat transfer stops when the two mediums reach the same temperature. It's kind of like the thermal equilibrium. Okay, when the two mediums reach the same temperature, then we assume, okay, that both of the mediums are in a steady equilibrium state. Okay, So heat can be transferred in three different modes. So there are three different, I repeat, there are three methods or modes of heat transfer process. Okay, this is like the one thing that you always have to remember. Okay, conduction, convection, and radiation. Okay, maybe I will just want to ask just to get you guys talking a bit. So I'll ask Amma, what is the conduction heat transfer process from which medium, or maybe you want to give example from which medium to which medium for conduction. I will call Marwan maybe. Marwan, can you try? What is the nature of a conduction process, from which medium, from fluid to solid, or from what, solid to gas? What do you think?
From solid to solid, I think.
Yes. Okay. From solid to another solid. When we have two like two material, we like apa tu, besi, like two solid, in a building. Okay. Not building, a wall or something like that. Okay, you have two two different types of material. So so if there are difference of temperature between those two materials, so there will be a conduction. Okay, conduction heat transfer process from one medium, one solid, to another one solid. Okay, another one, second one, convection. Involves what? Maybe Al Mansur Omar. Mansur Omar. Convection between which medium to which medium, you think? Al Mansur Omar, you are here? Can
Yes,
you?
doctor.
Yes. Okay, so what do you think? For convection process, is from which medium to what?
Not sure, doctor.
You have no idea? Is, or any example that you think that involves a convection process?
Um,
Whether for solid to fluid, or fluid to liquid, or liquid to gas? No idea.
uh, no idea.
Okay, it's okay. Okay, so convection normally is from fluid. So fluid, liquid, and gas. Between liquid to gas, or gas to fluid, or gas. Okay, that is convection. So convection normally also can occur naturally. There are two types of convection. Forced convection means that you put auxiliary power, electricity or etc., to the system, or it's naturally due to the ambience environment, the different temperature within the environment. So we can the convection process can occur. Or for example, now recently, we like more modern here, now right now, we have stove, gas stove for cooking at your home. So you that use this conduction and also convection process. Okay, the heat from the gas. Okay, the heat from the burn gas will transfer. Okay, the heat, the difference of the temperature to the anything that you want to cook in the stove, on the stove. Okay, and then radiation. This is a bit slightly different. Okay, so what is radiation? You can, anything about anything about radiation that you can think of. Maybe I'll call Afiq Zufairi.
Yes. Yes,
Apa
doctor.
tu radiation? Masa macam mesti dah pernah dengar kan. Radiation ni apa? At least apa yang awak terfikir?
Uh, uh, apa tu? Macam masak masak
Masak?
air and then
Aha.
like the heat from the stove macam radiation sampai ke sampai tempat yang nak masak tu lah.
Okay.
Electromagnetic wave, something.
That is the keyword. Okay. Okay, thank
Okay.
you. The medium, okay, the transfer medium for radiation, there is like a wave, electromagnetic wave. But so means that that there must be a heat source. Okay, when you have a radiation, normally on our ambience, the heat source is this main heat source come from the solar, the sun. Okay, so the sun can emits radiative heat transfer, electromagnetic wave. There is electromagnetic wave. When there is electromagnetic wave, so there will be this radiation heat transfer. Okay, emissivity. Okay. That relates to that. Okay, and then okay, so all modes of heat transfer require the existence of temperature difference. Okay. So in aerothermodynamics or aerospace, the one that relates with us, okay, normally is the convection, okay, because convection needs at least a fluid transfer from fluid to another fluid. Okay, so this convection process, heat transfer, that we will apply more. Conduction also some part, if you study about structure, aerospace structure, material structure, if you want to improvise the structure of the material of the aerospace aircraft engine, then maybe you need to take into consideration the conduction heat transfer process. Okay. And then okay, this is the normal situation. So you are normally interested in how long it takes for the hot coffee in a thermos bottle to cool to a certain temperature, which cannot be determined from a thermodynamic analysis alone. Okay, so if you have a hot coffee, a thermos bottle, so it is like insulation. So we expect less heat transfer, the slow heat transfer to the ambience outside to preserve the hot coffee. Okay, so when engineer or scientists design the thermos, okay, the insulation part, of course they need to consider one of them is the conductivity heat transfer of this thermos bottle material. Okay, so in order to design this thermos material, they need to consider the material that you're going to use. So this material how much the amount of conductivity heat transfer, so that we can use it, okay, as an insulation for the hot coffee, to preserve the hot coffee. So that is that part, the design consideration of the material of the thermos bottle use is is part of this thermodynamic knowledge. Okay. And then the other one is the natural cooling, heat flow of the hot coffee, a mug or a cup of hot coffee in a room or in a cool environment. So normally the heat from the hot coffee, 70 degrees Celsius, will be transferred, so the coffee will cool down naturally to the environment. Okay. Okay, so application of heat transfer. Okay, so of course there are a lot of application of heat transfer. So the first one, energy production and conversion. Okay, so to produce power, electrical power or mechanical power, we have a power plant at the industry. Okay, the main one is that they use steam. Okay, steam as the main working fluid in the power plant. So with that steam, so the steam will undergoes all the process: compression, evaporation, expansion, etc. And from there, we will produce power, okay, mechanical, electrical power to the generator. So that is one of the application of this heat transfer. So that involves heat transfer as well, the power plant. and also include, of course, the generation of thrust power for aircraft. Also, we need to consider this heat transfer, and then solar energy conversion or any other energy conversion, renewable energy conversion. Okay, so this is part of the heat transfer as well, because for example, solar energy, it converts the heat from the sun with radiation, etc. And there is also convection. Okay, so transfer the heat to the electricity or any other form of energy. Okay, so the conversion of the this renewable energy is also consider the heat transfer process. Okay, and refrigeration and air conditioning, heat pump, heater. Okay, those appliances in your house, at your hostel maybe. So those device also applies this thermodynamics heat transfer process. Okay, in the maybe second half of the semester, in a few chapters, chapters, we will see in details the process of the heat transfer or thermodynamics in refrigeration, air condition, and heat pump. Okay, so those involves heat transfer as well. Domestic applications are again oven, stove, toaster, cooling of electronic equipment to turbine cooling or cooling or any electronic device, our computer. Okay, so that involves heat transfer as well. Manufacturing materials, processing, automobiles, aircraft, just now, and nature. Okay, also naturally, our ambience environment also there's exists this heat transfer process. Okay, even though we don't have if we don't have electricity at our house, we just open up our window and there will be naturally air comes in to cool down to cool us or to cool our building. Okay. So, okay, application of heat transfer, human body, okay, us in human, okay. So we also can transfer this heat, okay. So obviously we eat, when we eat and we digest our food, etc. So we produce energy. So sometimes we produce heat as well without we apa okay, for example, like if we in a house, okay, the occupants in the house or in a building, okay, actually from their body they transfer some sort of a heat to the inside of the house. Okay, so human body as well can have this heat transfer process involves. Okay, and then air conditioning system, like mentioned just now, heating system, electronic equipment, power plant, in the industrial and refrigeration system. So some of the those are the application of the heat transfer process in our lives. So it's very important. Okay. Okay, some bit of the historical background. Okay, hot body to cold body just now. Okay. So from the kinetic part, okay, so kinetic, we mentioned kinetic is movement, okay, the movement of the kinetic energy, the motion. So treats molecules as tiny balls that are in motion and thus possess kinetic energy. Okay, so even though we can't see it, for example, especially in the convection process between fluid, liquid, gas, etc. So we imagine it's like the how the heat transfer process occur is that the molecules between those body, the hot and cold body, is in motion. Okay, so that kinetic energy from those molecules will transfer. Okay, heat. Okay, heat transfer process between those body. Okay, and then heat the energy associated with this. So we actually we measure this kinetic energy, motion of atoms, molecules. Okay, caloric theory, I think tak apa, to just another definition. So he is a fluid-like substance called the caloric that is massless, colorless, odorless, and tasteless. Okay, history. Okay, Joule. Okay, just want to introduce this. Okay, because the unit of for energy or heat transfer, the unit that the SI units that we use to measure this heat transfer or energy is Joule. Okay, so from this guy's name, James Prescott's Joule. Okay, so we use this unit to calculate, okay, the heat transfer or the amount of energy. Okay, Joule, energy in Joule. Okay, next part subtopic is about concerning the moving boundary work. Okay. Okay, so working system gas confined to a cylinder fitted with movable piston in thermal contact with a heat reservoir to exchange heat Q. Okay, so imagine if you have a piston, like in a piston engine. Okay, so and this piston is in contact with a reservoir. Okay, that has so it has a different heat, a different temperature between the piston and the reservoir. Okay, so that is where heat exchange will occur. Okay, once we have the contact and once we have the difference of temperature. And then initial state of the system. So we have to define normally the initial state and the final state of the system. So those are the most important parameter that we have to define for thermodynamics, especially is the pressure, volume, and temperature. Okay, pressure, volume, temperature. So once we know these parameters, pressure, volume, temperature, initial at the beginning and final state, so we can calculate, we can measure, evaluate the performance of the system. In this one is the piston engine with a thermal reservoir. Okay, so here it says if you have through absorption positive Q or release negative Q. So this work, okay, work or heat transfer Q, noted as Q is the heat transfer, the same unit. Okay, so Q is the heat, also in joule, and W is work, joule as well. So heat work is part of the energy, because energy also is energy that we will see later on for first law of thermodynamics, the energy balance. Energy also is in joule. Okay, so this they are in the same units. Okay, so they have direction actually. So it's like a vector actually. Okay, so they have a direction. So this direction that will tell you the direction of the work done or heat transfer. Okay, so if you have a positive value of Q, means that the heat is being absorbed by the system. If we consider our system is the piston. So, and if the heat transfer Q, heat of the piston is a positive value, for example 10 joule, so means that this piston absorb energy from the thermal reservoir, for example. Okay, if it's negative, means that the piston release energy. Okay, release energy. What you say? Release, reject energy, lost energy to the give the energy to the thermal reservoir. Maybe the piston is warmer than the thermal reservoir. So it release energy, give energy to the reservoir. Okay, of it by the system gas. Okay, also work can be done in raising the piston or lowering the piston. Okay, so we have a piston. So we can the work done, how the work is done is by compress and expand, compression and expansion. Okay, so if we compress, it's like we give can be done. Sorry, if we can be done in raising the piston positive. Okay, once we raise the piston, so is we give it's like expand the gas, the fluid in the piston. Okay, so imagine you have the piston inside the piston. So you can see the molecules, those tiny bits molecules. It's like the molecules of the fluid or gas inside the piston. So if we release, if you raise the piston, so the gas, the fluid inside the piston will inside the piston, the cylinder will be expanded. Okay, so this expansion will be measured as the positive work produced by the system, positive W work. If we lower, if we compress it, then the work done will be negative on the piston. Okay, so this is the equation, the main equation of the work, boundary work done, moving boundary work done. So it is integral of PdV. P is the pressure and V is the volume of the system. Here is the piston. Okay, so that's why we need to consider first what is our closed system. Okay, so we focus on the closed system, that, and then we know the direction of the heat transfer or the work done. So here work done is PdV. The integration of PdV means that we have to have this equation function of pressure. Okay, so once we have the equation function of pressure, so we can integrate it, kind of like that. Okay. And then here, okay, so some of the example of how do we measure this work, boundary work, work done with a diagram. Okay, ABC. Okay, so dW is that is the work. Okay, work also can be written as force times S is the, here S is the like the distance. Okay, force multiplied with the distance, the work done, or also this force is in pressure and area. PA is pressure and area. So this is force. S or ds is the distance, the tiny distance. Okay, so force times distance is also work done, or PA. Okay, because you know that the pressure force, okay, pressure is force over area. Okay, so we can also write this force in terms of PA, and then rearrange it, so we get the W. W is the boundary work done is the integration of PdV. Okay, so ds times with A is the volume, distance times area. Okay, so work done represented by the area under the curve on PV diagram. So for example, we have PV diagram. Okay, so once we have the PV diagram, we can sketch the process. Okay, from the initial point to the final point. So from the diagram, we can calculate the area. Okay, below. So this area will represent like integration, represent the work done by the systems. Okay. So also depends upon the path taken from I to F state. Okay, depends on the path. Okay, the process. Okay, from I to F. Okay, and then PV equals to nRT. So this is the ideal gas equation of state that I show you last week. Okay, ideal gas equation of state. But this one is in molecule. So sometimes we write it as PV RT like this in mass, or PV MRT, small v or big. Okay, V. Okay, so depends also on the equation, ideal gas equation of state, because there is P pressure in there and volume as well. Okay, from I to A, process volume increase at constant pressure. Okay, so imagine the second B diagram. Okay, we have this path. Okay, from I to A. So the process occur in pressure, constant pressure or isobar, and then continue from from A to F. Okay, so we have like to calculate one part and another part because the process is different than the first one A. Okay, the first one A, the process is direct from I to F. Okay, at a different temperature and maybe constant temperature, a different pressure, but maybe constant temperature. But here in B, the process started with a constant pressure and then constant volume from A to F. So the results of the work done is maybe different A and B, even though the final state is the same, but the process that occur throughout, okay, the path is different. So the work, the total work done is different. Okay. For last one, for process IAF, total work is done and net heat absorbed is Q minus Q. Okay, tak apa. Okay, so and another one is the C. Okay, you can also have this type of path process from I to F. Means the if you look at from this diagram, by conducting the process like C, the third diagram, maybe we produce less work. Okay, from diagram we can see that we produce less work. W is less, W positive. Okay, okay, another part moving model work. So the same one. So the expansion and compression work in a piston cylinder device. So for example, if you have a piston cylinder, okay, so the boundary work done is calculated using the integral of the PdV. Okay, so a gas does a differential amount of work as it forces the piston to move by differential amount ds. Okay, a small distance, we imagine a small distance of the pistons, the movement of the piston. Okay, and then while work positive or work negative. So positive normally is the expansion, because if we have a gas turbine cycle, okay, when we produce the process in the turbine expansion, when we produce work, it is expansion process. Okay, and then negative compression. So compressor, we need to pump, compress, give electricity, give power for the pump or for the compressor. So the work or power will be a negative, because we need to give provide release power or work to the system. Okay, the work associated with a moving boundary is called boundary work. Okay, so that is why we call it boundary work. This is the work within the closed systems of the gas, the fluid. Okay, the area under the process curve on the PV diagram represents the boundary work. Okay, so if we want to look at it closely, okay, the path between V1 to V2, 1 to 2. Okay, so the area, if we do integration, means that we do area, we calculate the area, the small area, dV. Okay, so those are the boundary work done. Okay. So tak apa, okay. So we can have a different path, WA, WB, WC. So it will produce different amount of work. Okay, depends on the path that we take. Like I mentioned just now, because if we don't use the same process, the same path, Okay, so means that the pressure, the temperature along the path will be different. So that's why the work in the end, the net work done according to the path is different. Okay, polytropic, isothermal, and isobaric process. Um, Okay, so there are different types of process done by this boundary work that can be done by this boundary work. The first one is polytropic, because so it is noted as C. Okay, the parameter, the parameter for this polytropic process. So, polytropic process, actually we seldom use this one, polytropic. So it's like we consider it's like the number, a parameter, number of n polytropic, this polytropic exponent as a constant. Okay, so it depends on this constant n. The different polytropic exponent will produce different work. Okay, but the one that we usually use is n equals to 1. So when n is equal to 1, so this is the isothermal process, the constant temperature process. Okay, this one is more regularly used. Okay, so we see the equation in the grey part. Yang atas tu tak apalah, okay. This one. Okay. So we can develop integrate this boundary work. For example, if the process occur along the throughout constant pressure. So when we have a constant pressure process, so the boundary work WB depends only on the volume, the difference of the volume. Okay, because if you see from the PV diagram, okay, if the process is occur in constant pressure, so the process will in the diagram, the process will be horizontal. Okay, on the straight line, horizontal, and constant pressure. So the only change is the volume, V2, V1. Okay, so in constant pressure process, the boundary work done only depends on the volume. So what is the boundary work for a constant volume process? Okay, what if we have a constant volume, PV? So constant volume will be like a vertical line from P1 to P2. Okay. So what if we have a constant volume? So if we look from the integral equation, okay, if dV, the difference of the volume is 0, constant volume. So the whole work, there will be no work done. The boundary work is 0. Okay, so because it's like we don't even give a release or don't raise the piston just now. It means that the expansion, the total the expansion and the compression balance the same amount. So the net work, the boundary work total will be 0. For example, like this, if we compress just now, we compress the piston in 10 joule, about 10 joule, and then we raise the piston, expand the gas, also about around 10 joule. So the net work, the boundary work total is 0, because the difference is the same. Okay, it means that the volume of the gas is back to normal. Earlier, initial state is maybe like 5 meter cube, and then when we give the same amount of work of expansion, raise the piston, so the total amount of volume of the gas inside the piston still will go back to the initial value. So there is no different volume, constant volume. So the boundary work, the work done, the net work done is zero. Okay. So work provides a link between force and energy. Okay. So for this one is the FDS just now. Okay, force and the displacement. Okay, also means that we either we use pressure and volume, pressure times volume. We can also calculate the work done, especially in solid mechanic work. Okay, to take into account the mechanical work in the solid, we can use this one FDS. Okay, instead of PV, because PV, pressure and volume, is more used in the fluid gas or liquid transfer process. Okay, so this is more on the solid mechanical. I think you have seen this in static or dynamic. Okay, so this is also work done. Okay, so we can calculate the work done by knowing the magnitude of the force times the magnitude of the displacement. Okay, but this one is seldom applied in this aerothermodynamics. Okay, kita tak guna yang ni tapi you still need to know about this because this involve the structure part. Okay. This gives no information about the time it took for the displacement to occur, the velocity or acceleration of the object. Okay, when we calculate the work, however, we don't have the information on the time, velocity, etc. Okay, so we only know about the total, the energy, the amount of energy work given to the system or released by the system. So this is the units of work, joule, or can also be written as Newton meter because Newton force just now and meter is the distance S. So Newton meter also in joule, or we can also rewrite in kilogram meter square per second square. Okay, so means that we have to have information of the mass, the distance or the area, meter square area, and distance as no distance, time, period of time when where the process occur. Okay, the period of time, tempo of the process from the initial to the final state. Okay, ni apa sih? Okay, the work done by a force is zero when the force is perpendicular to the displacer. Okay, this is about if we have constant volume just now. Okay, constant volume. So from the diagram we can see the process is vertical, along the vertical line, constant volume. So the work done is zero. So the same in the solid process also. Okay, the work done by a force is zero if the force emits or the force give to the system is perpendicular. Okay, to the of the material. Okay, so sama je dalam solid material pun, kalau kita guna FDS tu pun sama juga dia akan dan kalau direction of the force perpendicular to the system, sama juga dia akan dapat work dan zero juga. So sama dengan yang tadi tu work force. Okay, if there are multiple force acting on an object, the total work done is the amount of work done by each force. Okay, so we can the summation of the total of the force, okay, can be used to calculate the total work done of the whole system. Okay, work can be positive or negative. Okay. Okay, so when work is zero, the displacement is horizontal, force is vertical. Okay, So for example here, if you have apa tu panggil, like not a tank, but something like this, okay, move the water, okay, a tank of water. So if the force used to move this tank is the same amount and in the opposite direction of the weight, okay, force weight mg. So and the displacement is horizontal, okay. So the work done is actually zero, okay. The force is vertical but this displacement is horizontal, so it's like the thing, okay. It can't really the work is not being given to the whole system. Again, work can be positive or negative. When lifting the box, work will be negative if lowering the box. Okay, angkat berat when we lift the box, so we put some extra effort, work, and when we lower down, put down the box, so work will be negative. Okay, okay, the force will still be upward, but the displacement will be downward. Okay, so we put down, but the force is the opposite. The force given is the opposite of the weight of the box. So the force still will be outward, but it's just that we release release the work to the from the box when we lower the box to a table or to the ground. Okay. Work anticipative force. Work can be done by friction. Okay. So in most system, for example, the piston just now, actually there must be some sort of energy loss. So this energy loss can be due, one of them due to the friction of the object. So actually, if in a real situation, not an ideal one, real situation, for example, the movement of the piston in the cylinder just now, actually there should be some sort of friction, okay, between, for example, between the piston and the cylinder, okay. So that is one factor that maybe result in energy loss, okay, energy total loss in the work done, okay. So the actual work done is actually maybe less, okay, or maybe higher if you want to give the force, because due to the friction we need to increase our work, okay. Or if we want to release the work, so maybe less energy need to be given due to the friction. But an object goes into heating both the object and its environment. So this one part, this friction, this energy loss due to friction will be transfer the form into heating. Okay, so remember I said mentioned in the earlier that actually energy can't be destroyed or created, but it can only change form. Okay, energy cannot be destroyed or created, but it can change form. So that's why even though if we at the beginning we give work, for example total is 10 joule, but we in the end we receive back, for example, maybe only 8 8 joule. Okay, but so where is those other 2 joule, the difference? Okay, so that the remaining of the energy has been transformed to heat. So heat also is energy, joule. Okay, so another, the remaining another 2 joule, for example, is being changed the form into heat. Okay, due to the friction. Okay, some energy may be converted into sound, or even some can be converted into sound. Okay, and then power often also interested in the rate of in the rate at which the energy transfer takes place. Okay, so this power, we can calculate power. Power is the rate of energy. So means that once we have the work or the energy, the heat transfer, the amount of heat or the amount of work done by the systems, divide by the temperature it takes, the time it takes, the period of time. So we have this power, amount of power. We can calculate amount of power. What? So power is in watt. Okay, energy is in joule, power is in watt. Okay, so joule per second. Okay, watt, joule per second. So it is in kilogram, meter square, second square. Tengoklah. Tapi joule per second watt. Okay, so means that for example, the compressor just now, okay, the pump or compressor, the compressor need to receive, need energy and it need work, okay, to run the compressor. Okay, the work total given to the compressor, the work is actually the electricity power. Okay, so if we divide the work given to the compressor by time, so actually we have power, the amount of power. So this amount of power is the electricity power that we calculate. Okay, to know how much the electricity needed by the system, the power plant, the gas turbine, or any system. Okay, so power is joule per time second in watt. Okay, so US is okay. Kinetic energy. So one form of energy is the kinetic energy. So kinetic energy is the energy associated with the motion of an object. So once we have a motion of movement of object, so means that we have this kinetic energy. So kinetic energy is in 1/2 mv square. M is the mass and v is the velocity. V here is not the volume, but it is the velocity square. And then scalar quantity with the same unit as work. Okay, so it has the same unit. Kinetic energy is still in joule. Okay, so work is related to kinetic energy. So once the work done, so the object is in movement, so means that it also has a kinetic this kinetic energy. So work kinetic energy theorem. When work is done by a net force of on an object and the only change in the object is its speed, the work done is equal to the change in the object's kinetic energy. Okay, so if we have if we give work release the work to the object, and that it makes the work the object move. Okay, so means that the work actually done to the object is the kinetic energy, the movement, the change of the kinetic energy, the change of the movement of the object. Okay, so speed will increase if work is positive, speed will decrease if work is negative. Okay, so if we give work, so the movement of the object, the speed will increase. And then if we release, take out work from the object, less movement, so the speed of the object will decrease. Okay, so work negative, speed decrease, and work positive, speed will increase. Potential energy. Okay, so potential energy is associated with the position of the object within some system. Okay, so potential energy related with altitude, height. Okay, and also the gravitational force. So because the gravitational force relates with the height as well. So potential energy is a property of the system, not the object. A system is a collection of objects interacting by force or process that are internal to the system. Okay, so once we need to consider this potential energy in each system if we know the position, the change of the change in terms of position, the altitude, the height of the object. So once we have that, means that there is some sort of potential energy. For example, if we throw something from a certain height, okay, from a building, etc., so there is a potential energy occur from the because the object is being thrown from a higher position to lower position. So the change of the height position will affect this amount of potential energy to the object. Okay. Gravitational potential energy, okay, I mentioned just now. So this relates also with the gravitational force, the G, the value G, acceleration. Work and gravitational potential energy. So the potential energy, the formula, the equation is mgh. M is the mass, G is the gravitational force, and H is the height, the change, the total distance. Okay, the height, the total distance, or the delta y. Okay, between the first, the initial point to the final point. So the units for potential energy, so it's the same as work and kinetic energy. Okay. Conservation of mechanical energy. So is the main conservation of energy. So like I mentioned just now, conservation energy cannot be created nor destroyed. So this implies the this conservation of energy concept. Okay, means that the total energy, the mechanical energy throughout the process or to the systems is actually remain the same. It's just that the form of the energy will change from one form to another form. When we put work or when we give energy, we transfer heat. Okay, for example, like just now, for the piston, if we measure at the end the work or the energy, the work released by the system is less than the beginning, the work done at the beginning. So means that some amount of those work have been converted into heat. Okay, so it's not that the work is being thrown away or totally lost, etc., but the work from the energy from the beginning has been transferred to another form due to the friction, for example. Okay, conservation of energy. So from this principle of conservation of energy, we know that the total energy, the sum of the kinetic and potential energy of the system, initial, and final, must be the same. Okay. For example, like just now, like if we throw something, an object, to the ground. Okay, so at the beginning, the object, maybe in the initial state, at the beginning, it has a high potential energy, but very, very small amount of kinetic energy at the beginning. But towards the end, when it drops to the ground, okay, so the potential energy will decrease, but kinetic energy will increase because the movement of the object. Okay, the motion, the speed that the object has. Okay, when we throw the object, the speed increase. Okay, so kinetic energy increase. So, but the total, even though the potential energy change and the kinetic energy change, but the total of this energy, initial and final, should be the same. Okay, due to this conservation of energy law. Okay. Potential energy in a spring. Okay, so if you have a spring, so the work done by the spring, if you pull out the spring, so we can calculate the energy or the work done by the spring. So it is 1/2 kx square. K is the parameter. Okay, the Parameter depends on the material of the spring, the conductivity, okay, like the Hook law, okay. So you have this value k constant, and x is the distance uh, made from the if we compress or if we release the spring. So the distance, the change of the distance, this that will account for the elastic potential energy of the spring. Okay, work energy theorem including a spring. So the total work energy done by the spring. Okay, so we have the change of kinetic energy, the change of potential energy due to the gravitational, means due to the height. If the spring is at a certain position, a certain height, so there should be a certain amount of potential energy due to the gravitational acceleration speed. And another potential energy is the elastic potential energy. So there are two forms of potential energy. One is due to the gravitational, due to the height. Another form is due to the elasticity. Okay. So PE will now be used to denote the total potential energy of the system. Okay, PE is the potential energy. Okay, okay, now we are already 10:14. 1 minute. Before I continue next part, I think we take a break, a small break. Okay? Okay, everyone. If we take a break, so sekarang kita take a break. Oh, there are already 12 of you. 12 eh? Zainul Arifin yang tak ada tu. Okay. Okay, so we take a break. Okay, we take a break until 10:30, around 10:30. Okay, everyone? Before we continue again.
Okay, Doktor.
Okay, break ya. Okay, we resume back our class. Saturday. Okay. Okay, so all of you are here. Miza, Khairul Rusti.
Yes, Doctor.
Kalau panggil nama sikit. Okay, so we continue. Actually, I look at my slides. Actually, there's only one subtopic left, and then we will do some exercise tutorials. Okay. But I just actually I just look at my email just now. I have an urgent meeting at 11, but it's okay. I still will. I try to parallelly conduct class and join the meeting at the same time. So within the when you guys you guys do the tutorial, so I will take some time to join the urgent meeting at the same time. Okay, because I need to join that meeting. Okay. But okay. Anyway, we finish this slide. Transferring energy. Again, the energy can be transferred by work due to the work force apply to the system. If we move the system, if we push the object, so due to the work done by our pushing, the force that we apply, so the object will move, will make a displacement. So this displacement will result in a kinetic energy and work done. Okay, heat again, heat transferring energy through heat. Okay, so for example, the spoon becomes hot because some of the kinetic energy of the molecules in the coffee is transferred to the molecules of the spoon as internal energy. Okay, so imagine if you have a spoon, so it is a material that can transfer, a heat transfer process occur inside. Okay, so the heat from the hot coffee will be naturally transferred to the spoon. Okay, so the spoon will receive energy due to the kinetic energy movement of the molecules inside the coffee. Okay, imagine the collision of those molecules will result in the heat transfer process from the hot coffee to the spoon. Okay, so that is how the energy transfer by heat. Oops, sorry. Okay, balik. Okay. And then mechanical waves. Okay, mechanical waves. So a disturbance propagates through a medium. Example include sound, water, seismic, gempa bumi. So those phenomena or inside the water or sound has a mechanical wave transfer. Okay, so there is energy transfer due to this wave, sound wave, noise. Okay, so ada mechanical wave that propagates through the medium, water, sound, etc. Okay, and then electrical transmission, transfer by means of electrical current. Okay, so this one by using a device, so we give a power work to the device. So, and for example, this one is a hair dryer, so produce a heat. So the work given to the device will be transformed into a heat energy. Okay, electromagnetic radiation, any form of electromagnetic waves. Okay, I mentioned just now at the beginning. So and once we have normally a heat source, a light, a sun or light. Okay, there will be some sort of electromagnetic wave transfer. So due to this electromagnetic wave, radiative heat transfer process will occur. Okay, will happen. Okay, so lastly, and not last, okay, second last, about the conservation of energy. Okay, so remember again, energy cannot be created nor destroyed. Okay, so another word of saying is that this energy is conserved. conservation of energy is being conserved. Okay. If the total energy of the system does not remain constant, the energy must have crossed the boundary by some mechanism. Okay. It's like the energy has been transformed, like the example of the work done in the piston just now. Okay, maybe the work being given at the beginning is less than or more than the what is being the work in at the final state. Okay, so one factor is due to the energy loss due to the friction. Okay, that is means that the work, the energy at the beginning is being transformed to another form of energy. Okay, but the total work is still conserved the same. Applies to areas other than physics. Okay, we can apply also this concept of conservation of energy in even in chemical, okay, and other area. Okay, last one, this one, energy and mass, the Albert Einstein. Okay, this one, if we have to calculate the energy involved in the speed of light. Okay. Okay, tapi we seldom use this one. Okay, the last, okay. Okay, now we look at the example of exercise tutorial to solve this boundary work. Okay, the first one first. Okay, the first one is actually just you need to think about it. It is without calculation or only small calculation. Okay, so we read. Okay, a rigid tank contains air at 500 kilopascal and 150 degrees Celsius. Okay, as a result of heat transfer to the surroundings, the temperature and pressure inside the tank drop to 65 degrees Celsius. Okay, so from T1 150 to T2 65 and 400 kilopascal. So P1 500, P2 is 400. So it is not a constant pressure process. Okay, so respectively, determine the boundary work done during this process. So how much the boundary work, the WB just now, the moving boundary work throughout this process of this water in the rigid tank. Okay, so what do you think about this? Try to think about it, this exercise. Okay, maybe I will ask someone to analyze and explain in 1 minute. Try to digest first. And what do you think about it? Okay. As maybe, oops, maybe Eugene Raphael. Betul ke saya correct I pronounce your name? Eugene, are you here?
Yes, Doctor.
Okay. So what do you think about the first exercise? The first one. How do you calculate the work?
Using, I don't remember that.
Okay. The equation is WPDV. But what do you think? First analyze this problem. Okay, what do you think about the work done to this in this example process?
The work done always 0
Why?
because
Why? Okay, it's actually correct. You mentioned that the work is 0, but why?
Doctor, the volume is constant, so the delta volume will be 0, right?
Yes. Okay. The volume. Okay. Thank you, Eugene and Marwan. So the work done is 0. Okay, so that's why you don't need to calculate anything actually. This the first exercise. So that's why I ask you to just analyze it to understand the problem. Okay, so remember. Okay, but anyway, the equation, the expression for the boundary work is just now as WB, the integration of PDV. Remember, integral of PDV. So it depends on pressure and volume. Here the only change occur is the pressure, change in pressure, and also change in temperature. Okay, there's no change in volume. Okay, so dv is 0, so that's why the total work done, boundary work in this process is 0. Okay, no change in volume or constant volume process. Okay. No work being released or being done to this tank. Okay. Okay, exercise 2. A piston cylinder device initially contains 0.4 meter cube of air. So imagine the piston cylinder just now. So you have 0.4 meter cube of air inside. At 100 kilopascal and 80 degrees Celsius, the air is now compressed so the work given compressed to 0.1 meter cube in such a way that the temperature inside the cylinder remains constant. So this time the temperature is constant temperature means isothermal. So again, determining the work done, the boundary work done during this process. Okay, a piston. Okay, try to think about this one pula. Okay. You can start with the same equation W integral PDV. This one. Sorry pakai kat sini Okay. The boundary work. So how do we express this boundary work during this process? To try to think about it, saya bagi 1-2 minit, 1-2 minutes. Okay, one hint, you can use the ideal gas equation of state. Okay, so it means that you assume here the air inside the piston. Okay, the air is in ideal gas. Is ideal gas. So once we assume air is ideal gas, we can apply the ideal gas equation of state. Okay, later on I will call someone. Sekejap.